Slide 3 for college algebra, which is on page 354. This deals with properties of rational functions. First thing we need to talk about is the makeup of a rational function. You can see that r sub x, or r of x, is equal to p of x over q of x, meaning that we have a fraction. The problem is the fraction is not just numbers, it's going to be polynomials. Come down here, you can see that when we talk about domain of rational functions, it deals with the denominator only. So if we take x plus 5 in this first rational function, set it equal to 0, we find out that x can be anything but negative 5. With letter b there, if we take x squared minus 4 and we factor, it's difference of squares, we can see that x can be anything but negative 2 and 2. Letter C, x squared plus 1 is non-factorable. Because it's non-factorable, x can be all real numbers. And then in letter D, in terms of this one, first of all, the first expression shows you that x can't be 1. But then you can actually simplify this because the top is x squared minus 1 times x squared plus 1. And so the final function ends up being x plus 1. But even though you can reduce it, you have to take it from the beginning. And therefore x can't be 1 because if it were 1, the denominator would not exist. There are our same rules that we use, our transformation rules. You can see this is 1 over x minus 2 squared, where the plus 1 is a vertical shift where we're going to add 1 to the y's. The minus 2 is a really plus 2 that we can add to the x's. So here's what's happening. So here's the original graph, 1 over x squared. We're doing the minus 2 first, so we're going to add 2 to all the x's. So the negative 1, 1 becomes 1, 1. The 1, 1 becomes 3, 1. Then we deal with the plus 1, which means we add 1 to the y's, so we shift up 1, and we have 1, 2, and 3, 2. There are two types of asymptotes that we have to deal with in rational functions. One is called a vertical asymptote. What a vertical asymptote is basically what the domain can't be. So it's what x's can't be. So what we do here is we take our denominator, x minus 1, set it equals 0. We find x equals 1. Remember, this x equals 1 is the equation of a vertical line. But in this case, it becomes a dashed line because it's an asymptote. In other words, the graph can't cross past that 1. Come down here, even though this is a rational expression, the x squared plus 1, there are no values that make it 0, the denominator 0, so there are no vertical asymptotes. Come down here, we have x squared plus 4x minus 21, which we have to factor first. We then set each factor equal to 0, and we can see that we have a vertical asymptote at x equals negative 7 and x equals 3. The other type of asymptotes we have is a horizontal asymptote. And, there's 3 rules for horizontal asymptotes. The first rule is, and if you look at this is example 5 on page 360. If you look here, the leading exponential power on the numerator is to the 3rd power. The leading exponential power on the denominator is to the 5th power. Anytime the denominator leading power is higher than the numerator, then the horizontal asymptote is y equals 0. Second rule is that if we look at a rational expression and the leading exponential power on the top is the same as the leading exponential power on the bottom, then all we do is we take that top coefficient and put it over the bottom coefficient. And our horizontal asymptote is y equals 2. The third type is what I'm going to call a slant asymptote. And basically what happens here is the leading exponential power in the numerator is bigger than the leading exponential power in the denominator. So what we have to do is we have to take the denominator and long divide into the numerator, which is what I've done here. And so what happens is, first of all, we multiply by 3x, which gives us the 3x to the 4th minus 3x cubed plus 3x, we subtract it. We get 3x cubed minus x squared minus 3x plus 0. We then multiply by 3, and we get 3x cubed minus 3x squared plus 3. We subtract it. We don't need to go any further, because once we get an equation in slope-intercept form, and so this would be really y equals 3x plus 3, which I've written here, this becomes a slant asymptote. So all we're going to do is graph it. We start off with our 3 for our y-intercept, which is our b. We move up 3 and over 1 to get our second point, do dashed lines, and so there is our slant asymptote. So when we're dealing with rational functions, we have to calculate and see if we have any vertical asymptotes or horizontal asymptotes, and that's going to make it much easier for us to graph when we come into sections 5.4 and 5.5.